electrochemistry. I was just looking at that. The 11th. Yeah, 1 o'clock to 3:15. I'll put it up on D2L today. Okay, not doing a lab today. I'm going to go forward. We'll probably do a lab next week. But let me go forward with electrochemistry. We'll see if I can explain electrochemistry. All right. First, it's balancing. So if you were told, if you were given this copper solid plus aqueous that's what we need. Okay, write the half reactions. So can you see what the half reactions will be here? We're going to do the copper becoming Cu2 plus. And then the HNO3 becomes NO. Okay. So what you do next is balance them. Ignoring hydrogens and oxygens. And I think that's balanced as it is, so I can leave it. 3. Three oxygens here, 1 oxygen here. So how many H2Os do I need to put in here? I'm just trying to balance the oxygen. So I got 1 oxygen here, yes. I need 2 H2O over here. So that's balanced. H is next. I should say I'm doing this under acidic conditions. It's almost exactly the same for basic conditions. So H's. So I've got 2 H's here. I've only got 1 here. So I'm going to put 1 H plus here. And now everything is balanced. Okay. This is copper with enough electrons to make it neutral. This is copper missing a couple of electrons. So I have to put 2 electrons there. We're kind of balancing for charges. So 2 negative charges plus 2 plus a 2 plus gives us 0. And over here I have a positive charge here. So I need to put 1 electron over here. It's not charged. Okay. So since I put the electron, one thing to think of is since I put the electron on this side, for the next one I'm definitely putting it on the left side instead of the right. All right. now we balance electrons. Okay, so I'll balance charges by putting an electron there and 2 electrons there. The next one is actually balancing the electrons. So what do I need to do to make the electrons the same number?
Times 2 by
Multiply by 2. So I'm just going to multiply everything here by 2. 2 times 2 times 2 times 2, and 2 times 2 will be 4. Okay. I think that's it. So what you do is you cross out your electrons once you've got them balanced, and then just bring everything down. So I've got an arrow here, and on this side I have copper, 2 H pluses, 3, 2 NO, got Cu, 2 plus. So, and that's actually the answer. That's the balanced equation. If you do this under, let me do one more and I'll do it under basic conditions. So what if you're given basic conditions? What if you were given minus okay, it starts the same way. You just fix it at the end if it's basic. So my half reactions, there's chromium, so I'm going to go and then the manganese. Okay, first we balance everything that's not oxygen and hydrogen, but they're already balanced. We've got 1 chromium, 1 manganese, everything else is hydrogen and oxygen, so that's taken care of. Balance the oxygens using H2O. How many oxygens do I have on this side?
3.
3. How many over here? 4. I need 4 here and 2 here. Okay. Now the H plus. There's no H's down here. How many H's do I have here? 3, so I got a plus. 3 H plus. Okay, electrons. You got neutral chromium here. Actually, it's not. What's the charge on chromium here? Do you know? So OH is negative, and there's 3 of them. So this is 3 plus over here. Chromium over here is, you got 4 oxygens. So you've got a negative H charge for the oxygen, 2. So this is this -2, 4 -2 oxygens is going to make a total of -8. So I need 6 plus there. That was me finding the oxidation state. I did last time. Oxidation number. So if it's +3 here, and it's +6 here, where do the electrons go?
The right side.
Yep, and how many of them?
3.
Yep. 3 electrons. The electrons go on this side over here. How many electrons do I need here? Well, let's see. 4 -2s for the oxygen, so again, it's a -8. This -1 goes here, so this is +7. Here, I have -2 for the 2 oxygens, so -4. This equals 0 because there's no charge. Now it's +4. So this goes from +7 down to +4. So how many electrons do I need? 3. 4, 5, 6, 7. That's right. Okay. Next, we would balance the electrons, but they're already balanced. So what we do now is chop these out. And everything that's left will just break down. One of the. Notice I've got 2 H2s over here. Let me write those as separate. H2O. H2O plus H2O. And I have 1 H2O over here, so one of those will cancel. 3 electrons cancels 3 electrons. One of these H2Os cancels one of those H2Os. That's it, right? Nothing else cancels. So that's gone. So over here. So far, it's balanced for acidic conditions. You would just stop there for acidic conditions. Here for basic conditions, there's one more step. You neutralize any H plus you have by adding as many of those as you need. So how many of these am I going to add here to neutralize that and turn it into water?
6 oxygens.
OH, OH. Why do we still have 2 there? Well, I would have left it. H plus. Why did you do that? I'm terrible at this. This is the 3rd time this semester I've tried to do this on a class. Why did it have 4? Why did it have 4? Oh. added water, oh. So I need 2 of those. I need 4 of those. Right? That's what I did wrong. I need 4 oxygens, so that has to be 4, right? Right. I messed up that. And then this one. And this one. We need 4 oxygens here. We only have 3. That's right. And then the H's. Okay, the H's. I've got 2 H's there and 3 H's there, so I need to. And then this one, I think I need 6 H's. Four oxygens. Just 1, 2. Okay, the 2 oxygens there and 2 there, so the 2 is right. So that's what I had wrong. I don't know how I got that wrong. All right. Balance, balance, balance with H plus. So I put 5 H plus over there to balance these 5 H's, 2 there and 3 there. And now I have to balance those H plus. Does that look right? Let's do it right this time. It's right compared to what's here. But I'm totally cheating looking at this. Okay. All right. Even without looking at that, to get the charges to balance, they're completely neutral on this side. So to get this neutral, I have 5 pluses and 2 negatives, so I need 3 more negatives. So these neutralize each other. 3 negatives plus 2 more negatives is a total of 5 negatives, balanced with 5 positives. And then over here, completely neutral on this side. To make this side neutral, we have a negative charge and we have 4 positive charges. That will make this totally neutral. 3 negatives plus 1 more negative, total of 4 negative, balances to 5 positive. Okay. The electrons already cancel each other. One of the H2Os canceled. Cross out that 2. All right. I think I canceled the H pluses as well. So those cancel, and they cancel 4 out of 5 of those. So I'm crossing that out. I have an H2O. H plus. Okay, this is balanced for acidic conditions. Yes. one more step to make it basic conditions. You neutralize any H plus you have by adding as many OHs to both sides as you need. So I'm going to add one OH negative to this side, but I'm going to also add it to this side. You add it to both sides. OH negative, and this OH negative makes this H2O. But now I have two H2Os. Two H2Os, that's gone. And then I just bring all this down. I make this look harder than it is, I think. So your last step 7 here is the basic conditions. So that's the answer to this one. So basic conditions, you just have one more step. You add OH to both sides, the same number of OH to both sides, but the number that you're adding is what you need to cancel the H plus. I just can't do those clean. I make that look harder than it is, I think. Okay. So the first step for electrochemistry is to be able to balance these. Shifting gears from balancing. I think this discussion is long-winded just to show you a couple of basic things. But I have to describe the electrochemical cell. Essentially, an electrochemical cell is essentially a battery. So if you've certainly used AA's and AAA batteries, and even the batteries, the lithium-ion batteries are like this. So, I'll say, so the batteries you're used to are made to be tight and compact, but you can make an electrochemical cell in a lab using beakers and stuff. The general idea is if I actually sketched it, I should probably just you have a beaker, and then you have another beaker. This is called a salt bridge. That's called a salt bridge. Then you're also going to have metal. So this metal is Cu. I probably should have drawn that bigger, but that's copper, meaning Cu solid. That's made of the Cu solid. And for this cell, we've got silver over here, Ag, silver solid here. And here we AgNO3, but really it's Ag plus and NO3 minus. That's a silver nitrate solution. And over here we have copper nitrate. AgNO3. The salt bridge for this one is sodium nitrate. So like I said, this is long-winded just to describe something that's kind of simple. And here we have Cu. That's all the parts. So you can build something like this and make it compact and make a little battery out of it. But the idea is you get NO3 coming out of the salt bridge. You get Na plus coming out of the salt bridge. Contacting them. Ag plus is going from so the Ag ions that are in here actually come over here, and in the process of connecting to the rest of the silver metal, it undergoes this process. Ag plus loses an electron, so you have electrons going this way. Usually, there's a voltmeter right there. So electrons are coming all the way over here, and then they land on these coppers, and you get copper 2 plus. Got the electrons going the wrong way. Like I said, this is going to be long-winded just for me to sketch this. All right, so electrons are coming in here, and they go onto an Ag and turn it into neutral Ag. The Ag sticks to the metal cation. And then here, the 2 plus loses electrons. So the coppers are coming off and becoming 2 plus when they lose their electrons. So over here, you have so this is the reaction that's going on over here, and this is the reaction that's going on. Anyway, maybe you want to look at the diagram in the book. I knew trying to draw that would be cumbersome. But I didn't upload this, I should have. But that's just trying to sketch this out of the book, But what to pay attention to here is we have what we call the overall reaction, and that's just what I've been showing you before. This is a half reaction, and this is a half reaction. If you put them together, you have Cu and CuS, Ag plus becoming Cu2 plus becoming AgS. These, I guess I would say, is so this would be the overall reaction going on here. And you just take the 2 half reactions and put them together. So over here, you also typically write Cu solid becoming Cu2 plus. Okay. If I wanted to include the electron here, where would I write it? Left or right? Right side. I would put 2 electrons over here. And then over here, so these are the half reactions. So on this side I have Ag plus, aqueous, Ag solid. And on this side I would write the electron over here. So there's 2 half reactions. So is this oxidation or reduction going on here? It goes from neutral and it loses 2 electrons. Is that oxidation? I always tell y'all that it's easier to think for the reduction side. Ag goes from being plus down to 0. So this side reduction is happening. And this one, the charge is going from 0 up to 2 plus. And by convention, when you sketch one of these, you always do the oxidation on the left and the reduction on the right. So all of that just to say, one more thing. Oxidation on the left, reduction on the right. There's a summary way to write this. You would go, here's the copper plus, and you do a line. I'm going to say 1M, because for the standard, I'll get to what the standard is in a minute to do calculations. But the standard is always considered to be 1 molar. So this is 1 molar copper nitrate, and this is 1 molar silver nitrate. So I'll write that there because they typically put it there. Cu. So that's the oxidation side. And then to continue this, generally a thick bar. And then you write the other reaction on this side, the reduction side. So 1 molar AgNO3. Aqueous. And then the skinny bar, Ag solid over there. So you're sort of writing a summary of this here, copper becoming copper 2 plus. And over here, you're writing a summary of Ag plus becoming AgS. So again, long-winded way just to show you some conventions about this. You could be given this and told to write down the standard way of writing it. I suppose the nitrate would have to be involved there for you to see it. And I knew it would just be a long-winded way of doing that. So let me try. Let me try just throwing that out. Let's see if it makes sense. What if you had, as in what if you had a question you were asked? Like this. Aqueous. GCl2. That's aqueous. This is solid. I have to think how I would ask this. Maybe I would just do this. G2 plus CO. I'm going to ask this. G2 plus. What if I just did Mg and G2 plus? Oh, I see what's messing me up. What if I just did so what if I gave you that and said, write that in cell notation? And I guess I would have to say, okay, in this case, NO3 was the spectator ion. I guess I could have done that. Maybe that's better. Two, maybe here. CO3. This isn't balanced. Two there. There. Two irons, 6 chlorides, 3 okay, that's balanced. But now what we're going to say is, all right, can you see how to make this? Is my point. So you would just start with EGS, skinny line. We'll assume this is still standard. And then GCl2, nucleus, thick line, and then Fe3 plus. Since this is Cl3, this is Fe3 plus. Nucleus. CO3, skinny, I should say aqueous. I'm making this seem a lot more complicated than it really is. Solid. So if you were given that, could you build that out of it? I made that seem a lot more complicated than it is. I'll get some of these up online for y'all to practice. Okay, the other way around. What if I gave you I know they put some of this on the standardized test. So I'm going to go through. So skinny line, thick line. Yes. This is more tedious than it is hard to understand. You guys don't want that screen on? I'm just going to put y'all to sleep today anyway. That screen was on, wasn't it? It's just too boring and you didn't want the screen to look at. Okay, what if I gave you that and I said, give me the reaction that goes with this? This is the here's the cathode. So reduction is going on at the cathode, oxidation is going on at the anode. Could you do that? First of all, the half reactions. So if you kind of ignore the Cl, what if I said, here's one of the half reactions. It's that becomes Cr aqueous. Well, what's the charge on the Cr? 3 plus. 3 plus because I've got 3 chlorines on there. So that's the oxidation half reaction. The reduction is going to be C. What's the charge on copper?
2.
Yep. There's 2 chlorines on it, so it's 2 plus becomes copper solid. If I said, okay, there's the 2 reactions, I could write it like this. Cr solid. Aqueous. Cu solid. So I could write it like this. But from there, it's, if you just had this, and I said, give me the overall reaction balance, you would want to start with the 2 half reactions. The reason this seems so much more simple than this is because there are no oxygens to balance. Therefore, you're not going to introduce hydrogens to balance. So what I'm saying is, we can actually start here with step 5. It's when you have weird stuff like something like that. Is your ion, when you have one of those complex ions, that's when you have to start doing this stuff. So just realize the balancing can be a lot more simple. But let's say we have this, we break it into the half reaction. Where's the electrons here? Left or right?
Right.
Here, how many?
3.
3 electrons. So electrons on this side, we're going to need 2 of them. Okay, and next we've got to balance the electrons. So we balanced the charges, that's where we were. I've got 3 there and 2 here. I would just multiply it by 2 here and multiply by 3 here. So 2 times 3 is 6. And then multiply through here by 3. So 3 times 2 is 6. And then we would chop out the electrons. and bring the rest down. Two CR. Is if I stuck the CL in there, it would still balance. This would be CL2. So if I put the spectator in there, which is CL, we'd have 6 chlorines and 6 chlorines. So you could stick the spectator ion there too if you wanted to. Okay. I told you all of that. Questions on these are a lot easier than I'm making it seem. For some reason, balancing redox reactions has broke my brain this semester. All right, so now let me show you. It's going to tell you. Two equations. So let's say you had just going to sketch it this time. Salt bridge. Got your metal electrodes. Beaker. Here's 17.3. Was that 17.3? I should have left my diagram up. This was NO3 and sodium. This was and again, I'm going to say these are 1 molar. Okay, this is easier than I'm making it sound too. Okay, if you had that, you could find out what the potential is. AKA the volts across here. Usually the volts are written here, but you do that very easily. It's this equation. That's the A cell. Standard, the 0 means standard, and 1 molar is part of the definition of the standard. And you just look up those values. I wouldn't make you memorize them. So there is, I didn't put the table here, but there's a table in your book. And there's even more in the appendix. But I think I'll just give you these values as a problem if I give you problems on these, which I will. Table 17.1, I've got that in my handout here. In Appendix L, there's a ton more. There's a bunch more. Let me just do this. So what I'm saying is you just look this up. Cu2 plus, really, this is the wrong one. AG is the cathode. So the anode is on the left, the cathode is on the right. So what you've got going on over here is CU. What you've got going on over here is AG solid. So you look up the one for in the chart that has Cu2 plus going to Cus, Cu solid. So if I look that up and make sure I'm looking for the 2 plus, so I see on there this is what's listed in this chart. This reaction is what I see in this table. And yet it's backwards from the way it is here. If I fill this out with the electrons, I'd have 2 electrons there. But that's just the way they're tabulated. And if I look for the Ag plus, there it is. I see in there your book tells you that this is negative, so that takes care of this swapping. But you could think of it like this, not to confuse you. But the anode, since this is what's going on at the anode, and the number they give me in there, I should have written it down. Plus 3.4 or 0.34. But that's for this. Since we actually have this, you have to swap the sign out. But the way that's written, the negative, that's going to take care of it. It's going to force that to be negative. So what I've got here is 0.34. And these are V for volts. And then the cathode, what's here for this one, Ag, there we go. Plus. So you just look those up and plug them in. So again, a very long-winded way of showing you something that's actually very simple. What you get here one thing you can say about that is because this comes out positive, or actually, let me say that for next discussion. Now, I guess I'll say it now. This came out positive. I could have written plus 0.46 volts. I want to write this just kind of as a rule. It is possible to set up a cell, and let's stick with 1 molar as our standard. Standard means 1 molar, it also means room temperature, it also means atmospheric pressure, standard temperature and pressure, and 1 molar. But if you did these such that you had an E cell that was negative, the electrons wouldn't flow. All right, simple rule, again, simple stuff, it's just taking me a long time to solve. Okay, and 1 more equation. So there's this equation, very simple to use because you just look up the values and plug them in. The other equation to show you is this time without the 0 up here, without this circle up there. This is log base 10. And our old friend Q, the reaction quotient. This is the E cell from up here, so you can always calculate that. But this is standard conditions. This is non-standard. Non-standard here means at least one of the 2 sides is not 1 molar. Also possibly not room temperature is 298. That's 273 plus 25 degrees. 25 degrees C is standard temperature, which it has to be in Kelvin for this. So standard here, you were at 298 and 1 molar. If you're not at 1 molar for both of them, you use this. It's also possibly not. R here is the gas constant. T is temperature in Kelvin. F is Faraday's constant. And I'm not writing that up there. N, you need to know this. Number of electrons in the balance equation. But what we will use is, again, this is more simple than it is. Makes it seem complicated when you're talking so much. But did they leave that negative? Yeah. For standard. Standard temperature and standard pressure, you would have that much equals 0.0592 volts. So that actually simplifies to which is the way we will use it. Okay, and let me do a calculation with that, just to show you where you land. This is called the Nernst equation. So if I gave you a question, I'll write it the way they do it in the book. Fe2 plus aqueous, comma, 1.94 molar. So that's the molarity of the iron. And then CO2 plus aqueous, 0.15 molar plus Fe solid. All right, and then you're asked, okay, that's the overall reaction for an electrochemical cell. So your question is, what is E cell? What is this? So you look up the standards, and then what is N? Do you remember what N is?
Moles.
No, the N was moles for something we did last test. This time N is the number of electrons. So how many electrons are transferred here? We don't even really have to balance, you can see. This is +2, this is +2. So 2 electrons leave the cobalt, making it +2. Those 2 electrons go to the iron, making it neutral. But we could draw this out in balance, but you're going to end up with 2 electrons here. You see that it's 2? So in this case, N is 2. Q, this is solid. This is solid. You actually know what this is. It's just today's been so boring that you're not going to be able to think. Do you remember what I write for Q? Concentration of the reactants is CO2 plus. I'm not using the solids because they're solid. Now you realize you knew this, right? Concentration of the CO2 plus. It's just that, the reaction quotient. And the solids don't show up in it, so I've got this in the numerator and this in the denominator. And the concentration, the brackets just mean concentration. So this is the concentration of CO2 plus is this. And the concentration of Fe2 plus. So that's how you calculate that, and you take the log of it. The N is 2. You can calculate the E cell if you look these up for, so I look up, I'm going to see in there, I'm also going to see in there, so it might be in the appendix. Fe2 plus. There's also, just realize so you don't get messed up doing this. There's also in that list because this is a transition metal, it can take on different charges. So that's in the list. Fe2 plus is also in the list, so don't let that mess you up. Here it is. That's this one. If I look up cobalt, 2, negative 0.28. All right. Let me get some space over here. Cathode, anode. All right. To find this, we need to know which one is the anode and which one is the cathode. Anode is where oxidation is taking place. Cathode is where reduction is taking place. All right, so which one of these is reduction? I should say, I should say this just so we don't get confused. This is what's actually happening. That's what's actually happening. This is what was listed in the tables. All right, so this is the one where reduction is taking place. Do you see that? The charge on FE is going from +2 down to 0. So this is reduction, and this is oxidation. Reduction takes place at the cathode, so I'm putting -447 minus and -0.28. Negative that. There's a negative in there. So really it's -0.447 plus 0.28. I'll get the calculator out for this, but if I just go dumb, 447 plus 0.28, because I'll get it wrong if I don't. So one thing we know, at standard conditions, electron would not flow here because this is negative. So we just calculated this. Now we have to do minus. Make sure I got that right. The wrong one. In the books, they properly did that. 2 after the decimal, 3 after the decimal, so I really need to round that. So, okay. 0.15 to get Q. 0.15 divided by 1.4. I get 0.0773. I guess 777 because that's 2 significant figure. And now I want to take 0.77. Take the log of that. Log of that gives me 0.5 times 2 volts over 2 times negative 1.114. 0.592 divided by 2 times 4. Negative times a negative is positive. So plus 2. And they got I did something wrong with the log. This is example 17.7. Let's see where I went wrong. Oh, they did that. Add it to there. Yeah, I did this weird. Just to finish it though. Come out to both. That's what. So it comes out to okay, and because this ended up being negative, at those concentrations, this would not be spontaneous. Okay. I cannot make electrochemistry more exciting, but I promise all this is a good bit easier than I make it sound. I got some problems to practice from the back of the book, because I don't have them on DQL yet. But let me just throw a couple of them at you. So picture yourself being able to answer this question. Is that oxidation or reduction? Going from +3 down to 0, so that's reduction. Oxidation will have electrons on this side. So let me write this. Number 1, number 2, just has some of those. So look at 1, 2, and then 3. 3 is balancing. Also we get 11. So look at 11 on electrochemical cells. That's right in that standard form. And then okay. Yeah, and just leave that last thing. This type of calculation, I have to decide how I'm going to ask you those. So just look at those for now. All my talking today comes down to really those simple things. Look at those for now before I get them on D2L. You can calculate, maybe I'll overdo this. Probably have to do the thermodynamic before I do this. Yeah, I'll say using the Nernst equation, so a little more stuff to Friday. So anyway, long-winded introduction to electrochemical cells. Just look at those 4 problems for now. And I think I can finish what we're going to do with this chapter Friday, and then we'll do thermodynamics.